Hi guys, it's my pleasure to present you to this wonderful community, and thank you, Phil, for organizing this. So today's talk is going to be about my take on changing the world of high-performance computations using object-oriented languages. So little bit about myself. I started a while back I always was keen into low-level computing stuff and C++, and I happened to get into finance. And turns out finance industry is actually quite interesting for high-performance computations, where you need to run multiple simulations, and at the same time you want it to be flexible in terms of delivering your code to your clients, being traders. And at the same time, you don't want your code to be delivered once and optimized once. You in a continuous development cycle, because new things are coming up, and you need to take that into account, and you need to integrate them into your analytics, and this cycle just goes on and on. So a couple of years ago, I was looking at interesting technology called automatic differentiation. And this inspired me to look into a different approach, how we can do multiple simulations. Anyway, so I will just step through my slides. And first, I'm going to show you some application domains for this. Next, we're going to talk about existing approaches, following by some examples, how it can be done, with example of the source code changes you need to make. And I'm going to cover it with a real use case integration with a really big C++ project. Right. Anyway, so what are the application domain for this idea? So at the moment, we focus on embarrassingly parallel problems. So something like this might be familiar with you. So you have a set of data X, and you need to execute some kind of analytics on this set of data and return set of output Y. Now here is my complicated numerical calculations. This function, it represents something really big in your C++ object-oriented code, right? So it may call various objects, use various object abstractions, do lots of nicety and optimized stuff, perhaps, right? So, but at the end of the day, you want to process your set of input data and get a stream of outputs. Now, this could be an example of this could be Monte Carlo simulations, right? So if we're doing something like simulating our market, then we have X as a representing set of Monte Carlo simulations, and we apply our pricing functions to get values Y. We then average them and get the answer. It could be some kind of analysis, right? So you have your analytics and you want to see how your analytic behaves under different stress scenarios, some various input data. So it could also be represented like this. The second application we have in mind here is embarrassing parallel problems, but where you need to compute gradients. And what do I mean by this is something like this. So you have a loop over X. Again, you apply your analytics functions, you get the values for Y. But now you want to see a sensitivity of each element of Y with respect to each element of X, right? And the traditional and very well-known method to do just bump and revalue or finite difference method is you basically modify your one element at a time in your vector X, you apply your analytics and get yourself changes in Y. And you can see the number of calculations you need to do grows very fast. To jump forward a little bit, so this second loop, the second inner loop, can be optimized using automatic adjoint differentiation technique. This is a technique that allows us to convert my complicated numerical calculations into a function that is able not only calculate the values for y, but also in a constant time can calculate sensitivities for all x. So this is what initially sparked my my interest to this technology, because it really you can get rid of this inner loop, which is huge. But in the end, it turns out to be even wider than just speeding up calculation of risks or sensitivities. So where these problems can arise. So things like gradient descent optimization problem, or for example, machine learning training. When you train your neural networks, what you do, you calculate sensitivities with respect to neural network weights, and then you adjust them to reduce penalty function. So machine learning not only limited to deep neural networks, but it can contain more complicated functions. So this is also a good application for this. And besides, obviously, this is very useful in finance world, where the risks are called, the sensitivity is called hedges or risks, and used widely. So what the currently available tools we have to solve such problems? Obviously, we are very crafty with C++. We can write templates to reduce some abstractions. We can inline some commonly used functions. We can do caching, etc. So it's all still available. We can do multiprocessing. So nowadays, CPUs are going into more and more parallel world. We have many cores. And if you have a program that needs to be executed many times, you can launch multiple programs. I'll assign a subset of set to each process and let it run. So this has some disadvantages, because you then need to synchronize multiple processes together, and the caching on CPU is also not utilized really well, because these processes are completely segregated. They know nothing about each other, and the cache you have less cache utilization on CPU. Now we can do multi-threading. Multi-threading is great, right? So you can run one program across multiple CPU cores. But in C++, it's really difficult to do, right? Because you need to worry about memory safety. You need to think about all the mutex protections that do take place and hit you with performance penalty. And you have to be a very careful programmer, right? And some of the people in the industry, I'm sure they are not, right? And if you do have some issues in multi-threaded environment, it's most likely it's very difficult to troubleshoot. So now modern CPUs, they come up with a clever vectorization technique. So similar to video cards, similar to GPU, we have embedded vectorization in Intel CPU. We have now AVX 512 that supports 512 bits for one register. So it allows you to process 8 double precision variables in one go. Trouble is, if you rely on compiler to take advantage of this technology, it will try to vectorize your original function. So it will try to find vectorization patterns within your code. And this would yield sometimes unpleasant results, because not always you have perfect alignment of the vectors with the problems you're solving. So if the compiler tries to vectorize the problem for one sample, it's hard to do in stable fashion. Now you can do manual vectorization using AVX intrinsics. This it is possible to do, but it does become very unpleasant to work with, right? And then you still need to decide what variables needs to be vectorized and what variables don't need to be vectorized. And if you're writing a generic function, you can probably do it like a template, and that actually is an approach to do that. Yeah, so manual vectorization is an option. Now, Another popular choice is to do Cuda, Opencl, One API, etc. So these all these technologies, they are been around for quite some time. One API is reasonably new. It's the problem with them I see is it really relies on crafty programming. So you need to know what you can put in, and generally you cannot use all the possible features in C++. So, for example, virtual functions they're generally not available on Cuda and Opencl, One API, etc. And they have to think about memory management, all this kind of jazz. You can do it, but then the maintenance of the end result is getting more difficult, and obviously you need more specialized developers to do that. So could be a better way. So the stuff I really wanted as a practitioner, I want to write a humane C++ and get the best performance, right? So if I want to use STL containers and I want them to dynamically allocate memory and stuff, I want to be able to do that. I don't want to be thinking all the time that it can kill me my performance when I'm running this Monte Carlo loop. Multi-threading. I know many people and many organizations try to avoid multi-threading altogether, and for the very good reasons, because if you do have some issues, it's very difficult to troubleshoot, right? I want numerically stable AVX vectorization. Like I mentioned before, if vectors don't align perfectly, you get some numerical noise in your calculations, and having the numerical noise from one run to another is not really acceptable for regression tests, and perhaps in games it's not a problem, but in financial industry it is a problem. I want to be able to differentiate my programs. So I not only want to differentiate just the neural networks, which are pretty much like more or less defined format. I want to write an arbitrary program and be able to differentiate it with a constant time. And I want my code to be optimal. So Jit is very popular these days. And do you want to do Jit calculations for C++? And in some cases, yes, because at runtime, you have more information available. So the functions that you can build at runtime can take advantage of this information and be more optimal than the functions you can compile at prior execution compile time. No memory allocation penalty. So I know people have been fighting this performance penalties from memory allocators for ages now. I don't really think about it. It would be nice to just not to have any memory allocation penalty at all when I'm in the phase when I want to process a lot of data, right? NUMA. So this is something I did not know about for until a couple of years ago. But since CPUs are getting more and more CPU cores, all the manufacturers, they cannot really get you a uniform memory model where each CPU core can access each memory bank with the same latency and speed. So we do need to allocate some memory banks to particular CPU cores, and making sure that some memory allocated to one block and only being accessed from a particular thread from that core is somewhat difficult in C++, because you have to control, or you either do it explicitly and allocate the memory blocks explicitly, but what happens for all these std objects where memory allocation is just taking place and you don't really know where they are, or have limited control of that. And I don't want to start from scratch. I want to take advantage of what is already there. So, and I want to keep my code fairly easy to understand, fairly easy to extend. So I started this project this project when I started to look at automatic adjoint differentiation tools. So I'm going to talk more about that, but the main pattern used in this technology is operator overloading pattern. So what we do here, we have our original program, and it uses native double types for each values, for all the variables, numerical variables. And what we can do, we change that to something we call active double type. And on this active double type, we can override the behavior of each mathematical operation, so plus, star, minus, exponent, so on. We change that so that we can get access to something we call valuation graph. And valuation graph really gives us what are the sequence of operations executed by the original user program. And by having this sequence, we can then traverse it backwards and compute all the derivatives, but we'll talk about that later. So the main point here, we use operator overloading to extract all the sequence of operations that implemented by user program. So what it allows us to do? So the idea I had on top of this operator overloading pattern is to why don't we Jit compile functions that would replicate this valuation graph at runtime, obviously runtime. So let's look at the example. So we have a function f. It simply takes a, b, and c, multiplies a, b together, adds c. So we now want to declare a new function, a function we Jit compile. We call it f forward because it's going to work from inputs to outputs. It takes variables a, b, and c as the original function, and then immediately allocates them to some placement in memory. So here we have a vector v, and this vector v is going to maintain the values of all variables, all input, output, and intermediate results. So similarly to what a normal compiler would do, we will allocate positions for each a, b, and c variable inside this memory space. What happens next is the operator star, we changed its behavior. So we changed behavior, so it's not only goes and computes a times b, that's not that interesting. What it actually does in addition, it goes and writes line number 3 into our newly compiled JIT functions. So we allocate index 3 for intermediate result. We compute multiplication, and this is the work of operator star. Next, we execute plus. And the plus will do the similar stuff. So it will allocate, it will create a new element inside vector v. What I mean when you create, it just simply reserve the position inside v. Right? It will take the value at index 3 and add c together, and this is our result. So what did we actually achieve? We simply replicated the same calculations, and the original user program is perfectly capable to do the same thing. So what are the advantages of this JIT compiled kernels? We can use all the features in object-oriented programming. So we can do some dictionary lookups to resolve some dependencies. We can do dynamic memory allocations. We can resolve our objects via pointers or multiple pointers. And so we can call virtual functions. And all these performance penalties for these features are only applicable once, when we actually generate kernel functions. But once we have these kernels built, once we have this f forward function compiled in memory, we can call this a forward function for our raw inputs for A, B, and C. And these operators, they are no longer, they're just plain operators from the CPU, right? It's plain operations. So we don't have any, we kind of sift through all the logic. We removed all the virtual functions and all the other logic on top of in your software development paradigm. And we resulted in a concise list of actual operations you want to execute. So in the end, we don't have runtime overhead per sample, right? So we do pay the penalty for each of these features just once. And once we have them, we have that all results, and all the memory can be allocated in advance, so that vector v here, it can be allocated once, and then you can execute all your logic after that without calling memory allocation at all. So these kernel functions, they are completely segregated from the original user program. And this is a very nice feature because it makes them memory multi-thread safe, right? So even your original code wasn't multi-thread safe, right? Your original function might have included some dependencies that you don't know about. This function, the kernel function, it only operates on vector v memory. And you can allocate this vector for each thread, and then you can run it in multi-thread mode in safe fashion. So these functions, since we know we're going to process multiple samples of X, we can automatically generate these functions in vector form, right? So we're not trying to vectorize a function for one sample. We're not doing this. We know we're going to process 4 or 8 samples at a time. So all the operations we execute, all multiplications, so on and so on, they automatically are done in vector format. So, and for AVX2 instructions, that means we can do 4 double precision samples in one cycle. And for AVX 512, it's 8. Again, you have to adjust a little bit for CPU throttling here, but at least in theory, it should be 8 times faster than the Scala version. Now, here is a good observation. What also is now possible. When we're building these kernels, we can declare what our inputs are, and when we execute original user function, some of the calculations executed by original functions, they are not directly dependent, they're not directly or indirectly dependent on function inputs. So they can be cached, right? And if for normal program, you have to identify where this situation takes place and think how you can cache various results, here it's all done automatically for you. We can detect that C1, C2, C3 don't depend on X0, X1, and then you can pre-compute all the calculations that depend on this constant and hard code them in these JIT functions. So what are the problems with these kernel functions? They change at runtime. So if your runtime configuration changes, you have to rebuild these functions. These functions can be very big, right? Because even a simple loop from going from 1 to 1 million elements can generate you 1 million lines of code. JIT compilation time. If JIT compilation time is slower than the original runtime, the whole idea crashes. The whole idea doesn't work, right? So the JIT compilation time is crucial here. So this is where our product comes in. We call it Aed Compiler. It's actually playing 2 roles. So it's not only capable of doing derivatives, but it's also capable of just accelerating the calculations, as I stated earlier. And what we do, we produce directly machine code from operator overloading pattern. So every time your original code executes A plus B, our library gets this signal from your code, and it will generate a line of code that would execute this A plus B in memory, and it will write it in machine code that is directly executable on CPU. So we support AVX2 and AVX512 vectorizations. We do it in the streaming mode. So we never want to keep all the evaluation graph in memory because it's going to be prohibitive. So instead, what we do, we get operations as a stream to our library, and we in the background we convert that into machine code. So we work as a basically a streaming compiler. Okay, checkpointing and another very nice feature is we're able to then compress this code. And this is very crucial because, like I said, if you have a simple loop that does a million of iterations, you don't want to have a million of operations generated. You want to have some kind of way to compress that into smaller footprint. And that's important for not only memory consumption, but also for execution speed, for CPU to use less memory and better cache utilization in this case. Right. So enough me talking. So that's basically a rough idea and enough slides. I want to go and show you some code, C++ code, how it looks. Let me just change my sharing. Right. So this is a simple example of the library interface. What we want to do, we want to record original user relations, and we're going to keep them inside ADC function object. This function, once functions are recorded, once kernels are recorded, this function remains constant. So for the purpose of active type, we use I double, and it differs from the other Aed libraries in the sense that this I double is actually a drop-in replacement for double value. So internally, these objects, they contain values, double values. So you can use them as normal double value. And even if you're not interested in recording your evaluations, you can simply change double to I double, and you're going to get the same numerical results. It's going to work a little bit slower, but then again, you're paying the price for slowing down your initialization, but you're benefiting from running your simulations later. So in this example, we start with X, Y, and Z. These are going to be our inputs, and we use 0, 1, 0 as values during the recording stage. And we have variable f is going to contain our result. So we start the recording, and we mark X, Y, and Z as our inputs, and get yourself a handles to later on access these arguments. So in here, you can see that inside Y you have value 1, and the remaining is just static values. So the size of I double is actually equal to size of double. And we then run some kind of analytics. So this line can be very complicated, right? But for the purpose of very simple example, we're just doing this. And then we mark the output. We do stop recording. Once you hit the stop recording, after this, you have the kernels built in memory. And here we have two kernels. One kernel is going to replicate our calculations and arrive to the value of f for new x, y, and z. And the second kernel is the reverse kernel, is the kernel that's going to compute our adjoint derivatives. And it will allow us to go from gradient in f back to gradients in x, y, and z. So how do you use it? We need to create a workspace. So the workspace is the memory needed to run this algorithm. So it essentially contains the vector v from the slides. And as you can see, it's pre-allocated in advance. So you allocate all the memory needed to execute your algorithm, and you do it once. And then we set new values for x, y, and z. So we use the x, y, and z handles to populate values inside the workspace. We call forward. So once we call forward, we replicate all the evaluations through the evaluation graph. and we can print out results from the workspace. So we can say f of 1, 2, and 3. Note that this is a new values. So 1, 2, and 3, they are different from the original 0, 1, 0. And we can print out the value of f. So now for the differentiation part. So what do we want? We want to set gradient of f to 1 of our result, and we call reverse to execute adjoint differentiation on this graph. And okay, now it's done, and we can print out derivative of f with respect to x, y, and z in this point. Right? So this is a basic example for the interface. I will jump into something more interesting. So this example demonstrates how to use vectorization and run multiple simulations. So we have Monte Carlo using vectorization. In here, we again record the function called funmath. We allocate the memory needed to run this algorithm. And then we simply iterate inside the loop, given number of simulation. We set, every time we run one single simulation, we set new values for parameter x. We populate some random numbers, and we go forward. We accumulate the results for this integral and do similar stuff for gradient. So we set the gradient for the result equal to 1, we do reverse, and we accumulate the results for derivative of this integral with respect to parameter a. Please note here that we didn't really need to change the algorithm or the code for the user function funmath. So we have this pattern to follow, to record, to run, but this stays fixed. This stays more or less generic across other use cases. So I promised you free multithreading. So for free multithreading, what we do, we again record the kernels, and then we have a thread worker. And here you're basically free to use any multi-threading pattern you like. And since this ADC functions, the kernels we've built, they are guaranteed to be multi-thread safe as long as you use a thread local workspace. This is how you basically do it. We split full domain of the problem we need to calculate into chunks for each thread. We'll allocate workspace on each thread. We run simulation within one thread. Now it's all pretty standard stuff. So if the function is multi-thread safe, then it's easy to do. And then we simply just wait for all threads to join and print result, right? So, great. Now this example is a little bit different. This is for minimization, so we can use third-party minimization libraries, and within these libraries, what you're interested in is to calculate gradient. And since we are Aed library, we should be able to do it efficiently. And this is the function we submit to the third-party BFGS library. We again run forward from the inputs to the outputs, and we set gradient of the result to 1. We do the reverse, and we obtain a derivative of, in this case, dx dy. And the function we're trying to minimize is this. So this is the function we're trying to solve for this basic example. Right. So here is the simple example. And now sharing. Right. So how do you actually integrate this pattern into your code? One way of doing this is to template everything. So you had your analytics implemented using double value types. You can say my new type I'm dealing with is real, and it's a template. And I simply replace double with this real type everywhere. This is not ideal because it's probably will slow down your compilation times, and just introducing template arguments into existing code can cause some problems to address. Another way of doing this is just use typedef. So we again use a real type throughout, but we simply have somewhere in one place you have a typedef defining what value you want to use, and you can switch from native double to active double, or have like a conditional compilation if you like. This approach it's very easy to implement on existing code. You can simply change it in one place, and most likely you don't need to do much more. And I'll demonstrate that in a second. So for our case study on how easy it is and what the benefits are of this approach, we choose to use Quantlib, open source Quantlib library. So this is fairly famous in finance community. It has lots of contributors and lots of code written. We also picked OpenRisk engine, that is basically built on top of Quantlib. This is an engine that runs lots of Monte Carlo simulations and compute XVA. This is fairly intensive calculations that are quite relevant to current finance industry. And we want to demonstrate what we can achieve in this setting. Overall, we have a huge number of code lines. We had to change about 900 lines altogether to get it compiled and get it working. We see about 100 times speed up on a single core for this project, and I'm going to demonstrate it now. So first of all, this is the original ORE compiled as following their manual. And I'm going to run example 3, which is it's pricing some interest rate swaptions, and it's running Monte Carlo for the XVA purposes. So what it does here, it reads market data from XML files, and then it starts the Monte Carlo simulation. So here we're building Monte Carlo cube. So it's basically a 3-dimensional array of 5 traits, 83 time steps, and 10,000 Monte Carlo simulations. So now I'm going to talk about what we had to do to integrate with Quantlib. And in Quantlib, conveniently, they use a real typedef throughout their analytics. So we didn't even have to go and change double to some other type. So we have this conditional calculation, and it allows us to switch from active double type to native double type. In some cases, we had to do it for Boolean types as well, but it's going into too much detail, I guess. But essentially, we have active Boolean and active integer types if it's needed. So I'm now going to execute the same example using ORE and Quantlib built using AEDC. Right. So here we're solving the same problem. We recording one single Monte Carlo pass, and the recording takes about 1.3 seconds. The size in bytes for forward kernel is 9 megabytes. The reverse is basically nothing. We don't do sensitivities here. We're just interested in accelerating the loop. The worker rate memory is all the memory needed for that vector v. And this is all the constant data used in this function. So see, it's very similar to kind of report you get from a normal compiler. Now, we spent about 0.7 seconds to generate random numbers needed to drive this simulation. And then having these kernels, we build this cube of the same dimensions, and it takes 0.6 seconds to complete the loop. And this is using AVX2 and using one single Monte Carlo, one single CPU core. So if we're interested to speed it up further, we can easily do multi-threading. And if you look at the original program, it's still running. Yeah. So here we get this amazing results because we're able to really extract all the essence of all calculations. And we're able to do that and apply to a very large project. This project uses lots of C++ abstractions, perhaps in some cases it's not necessary and can be optimized. But at the same time, it demonstrates how you can take what's there, take what's built, and get a high performant system. And it's still running. Okay, I'm going to. I won't be able to wait for it to finish, so I'm going to stop it. Let me go back to my slides. Right, and we're really fond of AVX512 technology. It really can give you further 1.7 speed up if compared to AVX2. I know it doesn't look as much compared to 100 speed up we achieved on this code, but it's still a nice boost you get on top. So what did we do for integrating? So for the OpenRISC engine, this is how the original Monte Carlo loop looks like. We have a sample over all Monte Carlo simulations. So samples here is 10,000. We loop over a number of dates, and it's 83, I believe, and number of trades is 5. So for each date and trade, we run pricing and save it into this 3-dimensional cube. This is how we had to change it. It does look a little bit busy here on the screen, but it's very similar to what you saw before in the simple examples. We declare our ADC functions, the kernel objects to hold the kernels. We start the recording, and we simply execute one Monte Carlo path. So we're now looping over all dates, all trades, and execute original analytics to calculate prices. We then mark each output of each trade pricing function and mark it as an output and get a handle. So this trade res, it simply stores the handles for us to use later to run the simulation. And once the recording is over, we now allocate the workspace, all the memory needed to run all pricing, all trades, however different they are. They all can be processed in the same memory blob. And then we set new random numbers for each Monte Carlo path. We run forward function, and we populate results from the cube back to results to the cube from the workspace. And this is it, basically, right? And it was very limited changes we had to make to the original code base. which I remind you is quite large. Now, if you want to learn more about this, we have a couple of papers published. One is the very first one we did is in Wilmot. I think it's available free of charge to download. It's called Aed Breaking the Primary Barrier. Again, like I said, it's all started as Automatic Adjoint Differentiation library, but now we do see a wider application for this, just to simply accelerate various simulations, scenarios, analysis, etc. And we recently did analysis, joint analysis with Intel, running XVA simulations on Intel Xeon scalable processors. This is a fairly recent CPU with 56 cores, and we achieved very impressive scaling there, all for vectorization and multi-threading. Now, this project, the ADC project, we have early access program. So demo licenses are available. So do get in touch with myself or my team, and we're interested in various applications for this. We're looking for people to collaborate on. So if you're interested to work with us on this technology, we are planning to build interfaces for Kotlin and Rust, etc. We now already have Python, and we do see very good results if compared to other differentiation tools in Python world. Invest in us. We are planning another seed round fairly soon, and we are CIS eligible in the UK. I think I'm done. Unless there are some questions. I hope there are some questions.
We have one or two.
Yeah.
100. There's actually some that are very similar to each other, so I'm going to try and summarize some of them.
Yes.
There were a few people that were asking, when we were talking earlier on about operator overloading, whether you really just meant expression templates or something slightly different.
No. So we don't do expression templates. And the reason for this is because we don't need to. Expression templates, they are used to speed up, to basically compress calculations into on a level of assignment, right? So on one assignment level, you're aiming to compress that and let compiler to do the work on optimizing that. Now, we don't need that, and we can do a better job. So expression templates, they will slow down your compilation. Yeah, you can live with that, but if it's a big project, it's significant. And in addition, you don't actually need that as such with our approach, because in the end, at the end of the day, all operations are atomic on CPU. You can only do pluses, minuses, multiplications, and so on. You cannot really run a template expression on CPU in one CPU cycle, right? It's not possible. So we can, at runtime, do a fairly good job at optimizing the evaluations you execute on CPU. So no, you don't need expression templates. And one good example that wasn't very obvious to me from the very beginning, if you have linear expressions, so if you have an expression A equal B plus C, in typical AED tools, this would require additional memory stored for this expression. So you need to store basically 1 for each gradient, so the derivative of this expression with respect to B and C, and you need to store an index of B and C. And this you do for each assignment. But in our approach, we know this is the linear expression, and we don't need to store anything in our stack memory to replicate adjoint differentiation. But the code we generate, it can be compressed. So we really can get much better memory footprint than if compared to other traditional operator overloading AED tools.
Okay, thank you. There was a bit of a follow-up to that one, which is if you implement overloads of various operators for the I double type, do you also overload the mass functions such as sine and cosine?
Absolutely, yes. We overload them all. So you have to implement cosine exponents, and you have to implement adjoint versions of these functions. We even went as far as implementing some of them in more efficient assembly to get best performance from Intel chips. And another nice feature of this approach, our kernels can be essentially serialized and sent over for remote execution. So they don't require any additional external libraries to run.
Talking of libraries, there are quite a few questions comparing with other different libraries, but I think maybe the main one, because it came up twice, is asking about Halide. Can you compare with Halide? Do you know about that one?
I'm not that familiar with that library, to be honest. So we did compare ourselves with some open source, like the best state-of-the-art AED open source libraries. And we normally come back like 6 or like order of magnitude faster than them. And the reason for this is pretty much all the operator overloading AED libraries, they record data as data structure, and then you have some kind of interpreter to go over this data structure and update variables accordingly. Our CPU is the interpreter. So the CPU is capable of interpreting this tape and operations, and hence our performance is an order of magnitude faster.
Right. Yeah, digging into that a bit more. So there were various questions about this compiler stage. So you are actually generating assembly, and you're not using LLVM or something like that. You're doing this with your own Jit compiler.
Exactly. So we're not. I wouldn't say we generate assembly. Typically, people think about assembly as assembler commands in text format, and
Right,
this
so
is
the machine code. Yeah.
Yeah. So we go directly to machine code. We wanted to strike for the best compilation performance because, like I said, if compilation takes a significant amount of time, if compared to original evaluation, then the whole idea just breaks down, right? If it takes 1 hour to compile your kernels at runtime, it may and the original function takes to run 10 minutes. It doesn't make sense, right? So, and if you use off-the-shelf compilers such as LLVM, this would be the place. This would be the case, right? So we able to process very big relation graphs and very fast. And in our tests, we went as far as ahead as generating machine codes of multiple gigabytes to make sure it works and make sure that we still perform well. So yeah, we're able to generate assembly code for our internal purposes, right? So for development and stuff, to look at it. But in production, of course, you're interested into going to binary directly, and you're interested in doing that fast.
Yeah, I suppose you can consider assembly as the serialization format of machine code.
Yes. So just question is how long it takes to serialize, deserialize assembly, and
so someone was asking if you do peephole optimizations in the compiler.
okay, you need to. Okay, I'm not that familiar with what that is. Peephole.
Okay, maybe if Daniel can rephrase that, then maybe
yeah, I mean, feel free to contact me by email. I'm open to discussion.
And another question has just been upvoted to the top. How do you connect a detached variable to the tree? And will stud vector I double, maybe you need to read this one. Will a very large stud vector of I double cause memory allocation during the run?
Well, the compiler footprint is constant time of the original program. So if your vector of I double is huge, then we're going to consume basically maybe 2 or 3 times more than the original vector. but it's going to be the memory. The memory for the compiler is fixed constant of the original program. Unlike other AED tools, that basically the memory will grow with the number of iterations your algorithm executes, right? So once if you have some intermediate vector with a multitude elements, at some point in the algorithm, you may deallocate this vector, and we will release the memory accordingly.
About that peephole optimizations, I got some clarification. Recognizing specific patterns and rewriting them as you stream the instructions. Is that something you do in the streaming compiler?
Well, some patterns we do, some patterns we do recognize, and we rewrite them for best memory utilization, best registers utilization, and such, right?
Okay. Trying to think which ones we haven't had now. There was a more general question from quite early on. It may not make sense out of context, but what do you mean by differentiable programming?
Oh, differentiable programming is, if I start with this example. So when I have a function that is able to compute y from x, what I want to know is how y changes with respect to changes in x, right? And in this example, you can see that I can start bumping each element and x and rerunning the original program to achieve that effect. So this would give me what are the changes in y with respect to changes in x, right? And as you can see, the complexity of this algorithm, of this particular implementation, it is equal to the number of inputs. So if x is fairly large, 100, 1,000, a million, then you need to rerun your analytics similar number of times. And this is prohibitive, and adjoint differentiation allows you to do it in a constant time. And this can be observed in machine learning training, right? When you train your weights in your neural network, you have a lot of weights, and you want sensitivity to each of these weights, right? And if we would use this type of algorithm to train networks, it will be dead, right? On arrival, we won't be able to do anything, right? So we use a clever adjoint differentiation or backpropagation to obtain these differentials.
Okay, while you're on slide 3, the only question that actually referred to a slide, can you clarify about for all x on slide 3?
For?
It may be something you mentioned when you first went through it.
Right. So so basically we have a set of data, and each element within the set is a vector of data types, right? So we're mapping vector to vector, and we have an array of vectors to process. And given that the number of inputs in this vector is arbitrary, it can be 100, 10,000, then you go over each of these input, you perturb this input, applying shift of size h, some epsilon. You're rerunning your algorithm, and you subtract it, and you revert backward to the original value. You shouldn't be doing plus, equal, minus, equal. You should really record the value and then restore the value. But for the simplicity's sake, I did it this way for illustration purposes.
Right. So yeah. So perhaps it just meant every value in the inner vectors. Dennis, if you meant something different, just ask your question again. And might be easier if you can read this one in Remo, but what's the performance gain for, is it 2D order or second order, I imagine, second order derivatives versus Hessians versus bump and recalculate?
Yes. Okay, that's a very good question. So for the second order derivatives, I know some tools, they claim they give you a automatic differentiation for second order derivatives. The performance is really, Aed tool really can give you the performance of the first order differentiation. The second order differentiation, after extensive research, we came up to the conclusion that the second order differentiation is better to be executed using bump and revalue of the first order. So numerically, analytically, differentiating your code to second order is not that beneficial. I know some people are trying to do that, but it comes with a more tricky treatment for discontinuities. And if for first order derivative you need to think about delta functions, then for second order you even need to think about max 0x, and you have to do something special treatment there. So that just doesn't worth it. In our experiments, which we're happy to share, it's much nicer to apply first order derivatives and use bump and revalue for the Hessian.
Okay, thank you. And I think the final question, can you deal with conditional expressions such as if statements?
Yes, so if statements, thank you for that. It's a good question. If statements, you have two types of if statements. If the condition is stochastic, and what I mean by this, if condition is actually dependent on inputs to your function, then you have to do something about this condition, because it's possible that this condition will trigger for one set of input, but not the other. So you need to record both sides of this if statement. We have some tools to help you to find such cases. During the recording, we can identify this condition is actually stochastic and depend on your inputs, and can give you a report on these locations to address. If you come from differentiation world, these type of conditions are very good to be aware of, because they may result in incorrect derivatives. So I argue that if you're interested in computing correct gradients, then you need to know about these places, and you need to change them to essentially if function, or like a smooth transition between a left and right, or true and false values. Yeah, but in finance world, you usually don't have a lot of such cases. You do have a lot of if conditions, for loops, while, and such, but they don't depend on your inputs. An example of this could be if you have some kind of trade, and it works with particular cash flow dates. These cash flow dates, they are not changing, right? So you do some kind of interpolation in your market data, and finding the right bucket on the curve for this particular date doesn't depend on your random numbers. It doesn't depend on your path. It will always be the same, right? But places where it does depend is, for example, if you have, if you make a path, if you have like a path-dependent instrument, and you have a condition whether or not this trade was exercised or not. In this case, this Boolean flag inside the class, it needs to be converted into use active Boolean type. But it's fairly straightforward adaptation of the existing code.